Let's get started. So, hello everyone. It's my pleasure to introduce our speaker today, Shuolin Li. Shuolin is currently a postdoctoral research scientist at the Data Science Institute of Columbia University, and he's jointly advised by Professor Pierre Zhangting, Professor Tian Zheng, and Professor Ufman Law. His research focuses on developing process-based mathematical and physical models and data-driven machine learning techniques to study the Earth and environmental processes. Before joining Columbia University in July 2023, Dr. Li earned his PhD in fluid dynamics and hydrology and Master of Science in Computer Science from Duke University, where he was mentored by Professor Gabriel Couture. So we're very excited to have him share his insights with us today. And please join me welcome Shuolin.
Well, thanks, Yongchen, for the nice introduction. I know somehow like this is reflecting here. Let me turn it off. Okay. Good afternoon, everyone. Thank you for your presence. I'm Sean, currently a postdoc scientist at LEAP and the Data Science Institute, working with Pierre, Tian, and Manu. Today, I'm more than happy to talk about my research on probabilistic data assimilation and generative machine learning. So before getting started, I would like to mention that this work is still under development. So if you have any questions or opinions, that will be highly appreciated. We can discuss that in more details after this talk. So for today, I would like to talk about my research in these 5 parts. So part 1, I've introduced data assimilation and constrained this term in our domain. So after that, we can discuss state trajectory and distributions. For part 3, I'll introduce Lorenz 96, which is a simplified version of climate models as a toy model, and see how to demonstrate our probabilistic data assimilation techniques with this toy model. So for part 4, we'll talk about the parameter inference and the uncertainty quantification. Then for the last part, we'll talk about the application of this framework applied to extreme value estimation and joint quantile distribution analysis. Okay, first for data assimilation. So according to the standard definition, so DA combines observations from different sources with a numerical model's prediction to create an analysis that best represent the state truth of a system. So as you can see from the figure in the right here, so we have multiple observation in this red box. Then we also have a model which can generate some predictions shown in this black line. So data assimilation basically is a technique helps us to combine those observation and model prediction to generate some estimate of the state truth, and we call this estimation as analysis. To the best of our understanding, the analysis will approximate the state truth well. So why do we need that? So this is because let's look at this figure here. So let's say that the state truth is a cylinder. So according to different observation method or numerical models, we can only see a ladder of the truth, right? So here observation, we can't see the full picture. So meaning that for the observation, there are some errors. Similarly, for the numerical models, we also have some errors. So therefore, we need data assimilation, this technique. It combines observation with model prediction to generate an analysis data. And the analysis data is believed to have the best approximation of the state truth. Now this figure shows like a good visualization of the data assimilation technique. As you can see this line, which is a temperature observation. And the line here in several segment lines are predictions from the numerical models. So data assimilation basically says we need to infer the initial condition here, right? So that whenever we reach this point, we'll drag the model prediction closer to the observation so that the newly combined curve is the simulated line. This is just a visualization of a traditional data assimilation. Now, let's talk about a broad definition of data assimilation, which has been used a lot in climate models, especially in carbon cycle modeling. So the usual term here is also termed model data fusion. So as shown here, the usual description of the task of model data fusion or data assimilation in carbon cycle assimilation is to constrain the behavior of a model by requiring it to match some certain observations. So basically, this definition says, broadly speaking, for data assimilation, we can also think about this as a inverse problem of inferring the model parameters. So we can constrain or tune a model parameter so that the prediction of the model will match certain observations. This is because of two reasons. First, for climate models, the observations are usually very close to the state truth. And also these observations are direct, say that if we are interested in the precipitation, then our observation is precipitation. But in other cases, like more or less, if we are interested in the CO2 gases, sometimes we'll do some indirect measurement, such as like temperature, things like that. So those observations are indirect. But for the model considered in this talk, we'll focus on direct observation, so that in this case, data assimilation becomes a way of matching our models well to the observations shown in this red line. Cool. Now let's talk about state trajectories and distributions. So this figure here shows a current predictive ability of the weather forecast, as you can see in the top line. So for a 3-day forecast, the current weather forecast could be very accurate, almost like 100%. However, for the longer period prediction, say that for the 10-day forecast, the predictability is quite unreliable. It could be of several reasons. Of course, like the most straightforward reason we can see here is because those trajectories are highly random and chaotic. So if you look at the global temperature here, you can see that actually like the annual temperature is quite random and discursive. This reminds us like some features of turbulence, because in turbulent flow, we know that turbulence is unpredictable and highly random. But to some extent, the statistics of turbulent flows can be predicted, right? So because like climate models inherently is probabilistic, therefore we think that instead of predicting the trajectory itself, why not focusing on the statistics? As shown from the left figure, you can see that this is a distribution of the mean temperature, and those distributions are quite smooth, and the transition from one year to another is smooth, right? And also in the right, this is Earth's average temperature, and you can see those mean temperature are much more smoother compared to the temperature trajectories. Therefore, this gives us a motivation for this work in two parts. So part one, let's say that traditional weather data assimilation target state trajectories like temperature series, which exhibit random and chaotic behavior like turbulence. However, climate models are inherently probabilistic. Therefore, targeting long-term state distributions are more critical for accurate climate projections. On the other hand, so due to the increasing power of computational resources, like computer hardware get ever like growing, the ability like to generate accurate prediction becomes ever easier in recent years. So we asked, can we use some kind of machine learning techniques to help data assimilation? So to think about like state statistics, it reminds us the generative model, because generative machine learning models focus directly on the distribution of the data samples. Therefore, the question we have is, can we use generative machine learning to conduct data assimilation and use it for parameter inference with uncertainty quantification? And this is the motivation for this research. So the research goal of the current work is to develop a probabilistic data assimilation framework for parameter inference and uncertainty quantification. To do so, we will use Lorenz 96 chaotic system model as a toy model to train a distribution emulator conditioned on some physical parameters. So after that, we will infer the physical parameters from the observed state observations and quantify the parameter inference uncertainty by analyzing the sample distributions, which set the goal for this talk. Now let's look at Lorenz 96 chaotic system, and after that, we will introduce the probability distribution PDF-based emulator. So these two equations here basically shows the coupling equation of the Lorenz 96 dynamic system. As you can see here, it's comprised of two equations. One equation for xk, which is a large scale or slow variable. For yk, it is a small scale or fast variable. Those two variables basically are coupled by a coupling term here. So HBC are the coupling coefficient, and F here is an external forcing term. We call it climatic forcing. So as you can see from the first equation, so basically the statistics of xk, if you have like, let's say 6 or 10 different large scale variables, the statistics should be the same because there's no difference between each variable, right? And also this figure is a good visualization of the large scale variable in Lorenz 96 system. So what we are going to do is to use these two equations to generate some observation or the state truth. And later we will use these observations as a data set to train a PDF-based emulator. Okay, first let's look at some visualization of the Lorenz 96 system. So with f equals 18 or 20, we use 8 large-scale variable and 32 small-scale variable. Of course, like some good coefficient for the empirical coupling coefficients, we can generate this contour for xk because it's 18 different variables for there is a contour here. So according to this 2005 paper, they mentioned that this kind of coefficient choice will enable a real world replication. Okay, so in my model, I use like 4 large scale variable, then 18 small scale variable y here to generate the state truth. So first let the system run 4,000 model unit time. Here, the climatic forcing term is taken as 15, and other coefficients are the same as the 2005 paper. So as you can see from the bottom panel, which shows the trajectories of xk. So in the initial period, the trajectory is quite chaotic, while as time went by, so when we reaches like a time point after 3,000, then the behavior becomes regularized. That says like the system reaches a steady state, or at least quasi-steady state. Now, what we are going to do is to use the data after 3,000 to form a long-term distribution of the system and use this distribution as the observation truth for our data assimilation. And this figure basically shows F with different climatic forcing values. We can generate different distributions. Yeah. Here, like we tested climate forcing varying from 10 to 20 in a total of 500 scenarios to build the PDF emulator. Okay, so for the PDF emulator, we mentioned that we would like to explore the usage of generative models. So the first question we have is, what is generative machine learning model and why are they called generative? So some parts of this slides has been talked during our annual meeting, so we can go a little bit quicker here. So generative machine learning models attempt to produce a probability distribution PX that approximate that of the true data sample, and usually those data samples are quite complicated. They are called generative because the samples from PX generates new data, and this new data must resemble the distribution of the given data samples. And there are different types of generative machine learning models, such as generative adversarial neural network, variational autoencoder, diffusion model, and the normalizing flows. This slide shows an overview of these generative models. Again, generative adversarial network, VAE, variational autoencoder, flow-based model, and diffusion model. So what are the similarities for these models? As we can see from this figure, right? So these models are comprised of two parts, a forward process, right? Basically transform data from the physical space X into a latent space Z, yeah, wire neural network. So GAN use discriminator, while VAE use encoder. So flow-based model use forward flow, while diffusion model use like noise process. Then for the second half, we have like a reverse process, which basically replicate data from latent space to the physical space. And we hope that the generated data here could be a well replication of the data in the original physical space. So what is the fundamental goal of the generative machine learning models? We can see it from this figure here. So let's say that in a latent space Z, because it's generated from a simple distribution, usually a Gaussian distribution. Therefore, we can easily sample a point from the latent space. Let's say that we sampled a yellow box from the latent space Z. Then we pass it to the neural network. The neural network will give us a prediction shown in this area. So the prediction could be a tree, a cat, a dog, or a bird. So the ending goal here is to match the distribution formed by this image to the original given data distribution. So what do we mean by that? So let's say that if we have a black-white image of pixel 4x4, then in a 16-dimensional space, we could consider this image as a single point, right? So if we take all the image as points in high-dimensional space, then we can form a distribution. Then generative models basically match the distribution formed by this image to the original image space. And of course, we can do a conditional generative model shown in this image. So for example, when we are generating image from the neural network, we could say that we want a running dog at this condition and embed it into latent space, then we can generate some running dogs here. And the goal is still the same, to match the generated distribution with the true distribution. However, here we can condition the generation process on some parameters. We say this is a physical parameter that we have some knowledge about. Now, how does generative machine learning model works to optimize that generated distribution to the original sample distribution? The method is to use maximum likelihood estimation. So basically, MLE estimates the model parameter by maximizing the likelihood function, which assesses the probability of the observed data given certain parameter values. So what does this mean? So let's look at this figure. So let's say that we have a latent space variable Z, and we know the neural network has some parameter theta to be tuned. then the generated image could be taken as p theta x. Yeah, p theta x is like the posterior distribution generated from the neural network. Let's assume that there is a way to calculate p theta. So MLE basically says like we could determine the optimized theta star here by maximizing the products of p theta xi. Yeah, this is basically a description of maximum likelihood estimation in a realized way. Now, let's see how normalizing flow works using this method. So first question is, what is flow-based model and why are they called flow-based model? So the key idea for flow-based model is to map a distribution from a simple distribution we know how to generate and how to evaluate, right, to some complex distribution, which is our target, yeah, via some invertible transformations. And why does this work? This is because we can think about this process using a Jacobian equation. Suppose that we have two space Rn to Rn, right? And we know how the map is. We know x equals fz, right? So x and z are two different distributions. So using Jacobian equation, we can express the distribution of px as pz times a derivative, right? This is because px and pz, they are both distribution density functions. So the integration of x and z with respect to the samples will go to 1, right, on both sides. Therefore, we can move a derivative on the other hand. Yeah, this is how Jacobian work equation is. Now, let's see how Jacobi matrix is applied to the normalizing flow model. It's pretty straightforward, right? So consider a direct latent variable model over observed variables and with a latent space variable z. And we know for somehow there is a way to express the latent space to express the physical space variable x using latent space variable z, right? So f theta is like the parameter or a representation of the neural network. Yeah. Then we can just like apply the Jacobian equation, then express px using neural network and the Jacobian equation. It's pretty straightforward, right? Now we can see about this process more vividly using this image. Let's say that we are started with this simple distribution pz. It could be a Gaussian distribution as long as it has a simple form we know how to generate. Then according to the Jacobian equation, we can times this distribution with a Jacobian, with a partial derivative so that it transforms to a new distribution. Of course, and this derivative is modeled by a neural network. So we can we can apply the transformation multiple times until we reach the target distribution px, which is a complex distribution. That's basically how this equation means in terms of visualized normalizing flow model. Yeah. And of course, as we mentioned, we want to condition the model on some physical parameters so that we know how to generate some image based on the model parameters. Therefore, what we need is a conditional normalizing flow by including the physical parameters theta into the Jacobian matrix. And of course, if you do the math, you will find fundamentally the same. So we can explain this equation using this figure. So original normalizing flow starts from a single simple distribution, say Gaussian distribution, right? And reaches a targeted complex distribution. But for conditional normalizing flow, we are started with multiple different distributions conditioned on the model parameter theta simultaneously. Then we can use a neural network to transform these distributions together to a complex distribution so that we can generate a group of different distributions. Cool. And this is exactly a structure of the normalizing flow model that I used in my current work. As we mentioned that we can generate some truth distribution observations from the Lorenz 96 model, right? Then we can pass these distributions to the flow-based neural network. to transform the original physical space data into a latent space. Yeah, in the latent space, we can add the physical parameter that we want to condition this model on, right? On F, which is the climatic forcing term, then we can back infer the generated distribution. And we hope the generated distribution could be a good replication of the original data distribution. And of course, the inverse process is based on the inverse normalizing flow, which is a neural network we have already trained in the forward process. Yeah, and this equation shows the loss function that we used in the normalizing flow. So you can see here log px, which is marginal distribution we want to maximize, right? But if you take the log minus log, then it becomes a function to be minimized. Then after plug in the neural network, we will find that it essentially minimizing the latent space distribution plus the neural network, so that we can directly generate the distribution of those data set. Yeah, and the emulated result is shown in this figure. Here, those black bins are the true observations with different climate forcing term. Here we have like F equals, for the first one, we have 12.440. Then for these 9 figures, we consider the 9 randomly generated cases. And the red area highlights the prediction from the normalizing flow models. If you look at these distributions closely, we'll find that actually like normalizing flow provides a quite good way of predicting the distribution. This is a result for part 1, PDF emulator. Now let's talk about parameter inference and uncertainty quantification. So the first thing for uncertainty quantification or parameter inference is to figure out a way to calculate the difference between 2 different data samples. As you can see from the image, we have 4 clusters of different samples, right? So how to calculate or how to compare the difference between the green and pink data points? Of course, the first way pops up in our mind is to use a KF divergence, which is could be considered as a distance between 2 different distributions. And the calculation equation is shown here. So here, basically, KF divergence measures the distance between 2 different distributions. However, there is a potential problem that we cannot use this KF divergence for difference evaluation. This is because, as you can see from this equation, it requires P and Q samples from different distributions, right? It requires this calculation all the time. That means these 2 samples must have the same size. If we have different sizes, we cannot use KF divergence. That could be a potential problem. So what we used in our work is the maximum mean discrepancy loss. So this loss is flexible as it measures the distance between 2 feature means shown from this equation here. So in this case, like we don't care about the sample sizes. All we care is like the sample means, right? So with this formulation, we can easily calculate the difference between 2 distributions. And you can see from the right figure here, we have 2 different distributions, Px and Qy. So we can randomly generate some points for X. Let's say we have 10 points, while for Y, we could have like 9 or 8 points. But with the MMD, we can still calculate the difference between these 2 samples. Cool. Now, this figure shows how do we apply the MMD loss for the parameter inference. Yeah, so let's say that we have a well-tuned PDF emulator. So we sampled a data point from the latent space Z. Then we can pass these samples to normalizing flow. The normalizing flow will generate us a distribution, right? So of course, we can generate latent space variables multiple times, like giving a prior distribution. in that case, we will have a group of different distributions in the generated domain, right? Now, the thing is to match the given observation to the distribution generated by the neural network. Yeah. So how do we use it? Like we can calculate the MMD loss between the observed distribution with the generated distribution, right? Then using gradient descent to calculate to minimize the loss so that we can infer the model parameter f. Yeah, and this plot shows the parameter inference result for 3 different cases. So here, again, those black bins are the observations from the truth. We have different f values here, of course, and then we give these distributions as our observation. We want to infer the climate forcing term for these distributions. So we calculate the MMD loss between the observations with the generated ensemble distributions. And we'll find that the loss actually decreases and increases. So there is a global minimum region for each of the plots that basically says the best estimate parameter is around those values, right? This you can see here. Those, for example, let's take a look at the first image. So the optimized f is 12.32, while the truth we know is 14.40. So somehow this image are close enough to our tolerance. So we said that parameter inference works. Now let's talk about uncertainty quantification. So uncertainty quantification basically is to estimate the posterior distribution of the model parameter f given the data xk, right? So using a Bayesian framework, we can show that the posterior distribution is proportional to the conditional distribution pxk given fj, and prior distribution pf, which is parameter distribution. So for traditional data assimilation, what we work is to assume that there is a prior distribution for the prior, right? Then we can calculate the conditional distribution of pxk given f using the model framework. In that case, we will get a posterior distribution. However, here, using generative machine learning, especially the normalizing flow models, we can directly quantify the conditional distribution. So here, because from normalizing flow model, basically it generates a sample distribution, right? So we're not generating a trajectory. Instead, we generate a distribution of different samples. So by taking different sample sizes, we can get an ensemble projections. That means we already provided with the conditional distribution with uncertainty. Therefore, we can calculate the distribution of the observation with respect to the generated observation from the neural network, so that we can minimize the model parameter. And this is how the uncertainty quantification works in the current framework. This figure shows the uncertainty quantification result of the normalizing flow model. Again, we are provided with 3 different observations shown in the bottom, and black bins are observation, and the red area highlight the predicted results from the normalizing flow model. So here, because of sample sizes difference, we can generate multiple different distributions. That means that it will give us a way to quantify uncertainty. And here, those blue bands quantify the uncertainty of this estimation. And of course, here in the bottom image, the red dashed curve highlights the optimized result. For the uncertainty quantification, for the blue bands, these predictions are corresponding to F distribution shown in the top panel. Here, you can see that the truth is given in this red arrow, while the optimized prediction is in the peak of the PDF, right? Shown in these values. Still, like this is more or less 12.4, and here is 12.24. so close enough to the truth. Yeah, so this framework gives us a way to do uncertainty quantification. Now, let's talk about the application of the proposed probabilistic data assimilation framework for extreme value estimation and joint quantile analysis. So for extreme value estimation, basically, we are trying to answer the questions like, what is the probability of experiencing a 40-ish day based on some historical observations? So let's still take those 3 randomly generated samples as an example to illustrate this method. So mathematically speaking, the probability of experiencing a 40-day is like we give a range. Let's say that we know the lower limit here, XA, of a prediction, and also the higher limit, say like 40 each day, let's say that it's between 30, 35. 35 is not too high. It's like a 38 to 42, right? So we have a range for XA equals 38 to XB 42. We want to estimate the probability of such event within this range. Therefore, we can directly integrate it from the predictions, from the PDF predictions, because this is a band, so that we can get a range for the underlying areas. As you can see from, let's say, from the first image, the red area basically underlines the probability from the integration, right? So the lower bound should come from here, right? This is a small possibility. And for the higher bound, it touches the top of the envelope. So we have like a maximum probability. Then for the middle image, say that for X in the range of 12 and 13, between 12 and 13, we know the probability is between 4.4% to 12.5%. This is one application for extreme event estimation. Moreover, this framework can also be used for joint quantile analysis. So from statistics, the 2.5% and 97.5% quantiles the lower and the upper extreme of a distribution. So analyzing the joint distribution will help understand the likelihood of joint extreme events, of course. Like in climate risk, we are interested in the concurrent possibility of extreme heat and cold events. In hydrological risk, could be simultaneous flooding and drought events. And the joint quantile analysis is shown in those 3 contours. Again, this vertical line outlined the 97.5 percentile, while the bottom showed the 2.5 percentile. And you can see the joint distribution actually varies a lot for different physical parameters. Yep, and now it comes to the conclusion of this talk. So overall, we have talked about a probabilistic simulation framework that targets distributions of the state variables other than the trajectories. So for the first part, we have built a PDF emulator for Lorenz 96 chaotic system as a toy model to demonstrate the method. After that, we have built a framework for parameter inference with uncertainty quantification. And finally, we talk about the application of this framework for probability density function matching, extreme event estimation, and joint quantile analysis. And yeah, last, there are still some further work to be conducted. For example, the current Lorenz 96 climate model may not be a realistic one. So application of this framework to a more realistic climate models is needed. The ending goal is to improve the long-term state distribution prediction in climate models, which in the end will help us provide a better prediction, a better predictive ability for the climate projections. Yeah, that's it. With that, I would like to thanks for your attention. I'm happy to take questions.
If you have any questions, I can run the mic. If you have questions online, you can use the raise hand function or just pop a question into the chat.
Thank you so much for the talk, Sean. One question that I haven't completely understood, maybe it's stupid, but so for the Lorenz 96 generator, for a specific forcing F, the output is deterministic, or can you sample basically various?
Yes, this is a very good question. So actually, yes. So for a specific, okay, let me go back to the basic image. So here, for a specific F, from the normalizing flow model, so we generate a distribution, right? So to go from a distribution to those samples from those distributions, we need to sample it, right? So by using different sample sizes, we generate different group of samples so that we can form a slightly different distributions.
Okay, so sorry that I need to ask again. So I meant more so in the ground truth, right? And the data that you generate at the start. There was just wondering how you get sort of this uncertainty in there. I was just afraid that potentially, right, if you have for each F, like a single trajectory basically as observations, like how do you make sure that you don't overfit, let's say? Yeah, that's a good question. That's because like, as we mentioned in your neural network, I think like there is a very good could be a very good like representation like in the slide that I gave in the lip talk. So as we mentioned that like the replication from the generative machine learning, right? The point generated here is just like a mean from a group of Gaussian distribution. It's not like a yes or no question. It's a group like because there is no identical image, right? So with the mean, we can have different variants so that we can form different distributions. So you're matching the means?
Yeah.
And how do you make sure that then the variances are accurate?
Yeah, that's a good question. Just like common like generative model and machine learning models, right? Once they assume that there is a Gaussian distribution for the latent space variable, somehow they are fitting the latent space variable's distribution by deciding the variance and the mean from the forward process. We are tuning the physical space to the latent space, right? So you are generated mean and variance of this model. We are passing the mean and variance to generate a new image. So the variance and the mean already considered in the forward process. Does that answer the question?
Then it's not necessary that you're lost, basically, because you had the mean discrepancy, right? As the loss, it still incorporates also somehow the variance.
Yeah, yes, exactly.
Okay, thanks.
Sure.
We do have a few questions online, but I'm going to start with Qingyuan Yang's. Did you train based on all the X's or one X at a time? And then, do you want one question at a time?
I'll do one by one. Yeah. I think like I train it simultaneously based on different multiple different distributions simultaneously. Yeah.
Okay. And the second question is, how is the performance of the method likely affected by the increased number of parameters to estimate?
Yeah, that's a very good question. So we haven't explored that yet. So currently in our framework, we only condition the model parameters on F, which is a single climate forcing term. And of course, in the future, we could get more parameters as a condition to explore it. Yeah.
Great. And we do have someone online. Feel free to unmute yourself.
Hi, Shorting, can you hear me?
Yes.
Okay. Yeah, good talk. So I have one question. Can you go to your last slide, the conclusion slide? Yes, this one. Yeah, so I have a question about the first one. So you want to model the target distribution instead of the trajectories. But as we know, the trajectories is kind of a time series is a function of time. But for the target distribution, so if we model let's say if we call the state X, then we want to model the distribution of the state Px. But as you said, like if you are using the dynamic model, the Lorenz 96, then I believe the distribution of Px is also a function of the time. So it's a dynamic distribution, right?
So yeah, this is a very good question, but like let me clarify it a little bit. So here, yeah, Lorenz 96, of course, is a dynamic system, but the distribution we consider here is not dynamic because as we mentioned here, we have the system. Okay, let me go to this plot. Yeah. So we have let the system run like for 1,000 times, right? So we say that because the initial period is highly chaotic, so we only take the last period as our as the observations to generate state distributions. So the state distributions are fixed. It changes with respect to climate force F, not with respect to time. Does that answer your question?
Yes, that answered my question. Yes. Okay, but how can it be used for data assimilation? So traditional data assimilation is that we have the model prediction, we have the observation. Then we want to use the observation to update the prediction at this time, right? At the same time, yes.
Yeah. This is also a very good question. That's why like we clarify that a little bit in the beginning of this talk. We say that so this is exactly what you described is a conventional or standard data simulation, but more or less in carbon cycle modeling, data simulation is like more broadly defined. It's more like constrain the model parameters so that the prediction of your model could match certain observations. Yeah, shown in this perspective paper. So it's kind of
okay. So you are tackling an inverse problem for the model parameters.
Yes, exactly.
Okay. Not the sequential data simulation.
Nope.
Okay.
Yep.
Okay, thank you.
Sure. Question.
I'll just ask a follow-up to the question that was asked because I think that was a confusion in my head as well. Work here, that's great.
Thank
what
you.
I'm wondering is that is it possible to expand it to time varying systems? Because even the cartoon that you showed the slide before this, we have one model trajectory and one trajectory that you can match with.
Yeah.
In real world, you can imagine that the whole thing is probabilistic.
Yeah.
The model has an ensemble, the observations in the ensemble. Move the observations to more within
Yeah.
Is that possible?
Yeah, I would say yes. So actually, like my co-authors, like Yongchen, he has a very good work on like a more realistic way of data simulation. So he has like here we have like observations here. Like so in this work, what we did is to match those distributions, right? So in standard this data simulation, as like our co-author Yongchen did, is we also have some external observations. Of course, we need these generative machine learning models to generate the state truths, right? No, to generate the prediction, right? Also, we can combine the external observations and machine learning models so that to predict some state trajectories. And that is more like a dynamic way of doing data simulation. Yeah, and for this work, I would say that we can apply this work to a more realistic system using a traditional way of data simulation by targeting at the precipitation data, right? So think about like global precipitation data, right? It's like we could generate a distribution because it's spatially distributed, right? We can generate a distribution for each time point, right? We also have like some indirect observation like humidity data, right? Or temperature. And the goal will become try to use this framework conditioned on humidity to predict the evolution of precipitation distribution over time. In that case, it becomes a more realistic and direct way of conducting data assimilation.
Yeah. I have a second question. So you had a slide where you showed a few different frameworks, like GANs, VAEs.
Sure.
So then you picked normalizing flows. I was just curious why that choice was made. Is that the one that fits best with the way you're working, or do you do it in any of them?
Yeah, this is a very good question. So actually, like VAE, this is the first model we learned, right, in machine learning courses, because it's most straightforward, like autoencoder. However, like different from autoencoder, they have a way to do some like latent space matching. This is how VAE works. This model has been used a lot. I would say that in climate emulation. And for GAN, this model was quite popular before, like diffusion model. There's like a discussion you read it, like someone believed that this was the most powerful machine learning model they have seen like for the past 10 years before diffusion model. So basically, for a flow-based model, like a diffusion model, they are fundamentally the same, I would say, because like as shown here, we have a forward process, right? For diffusion models, this forward process mimic the Jacobian equation, which is like the gradient, take the gradient, right? The gradient process. While for diffusion model, you add noise one by one, fundamentally the same, but the physical meaning is different. And another difference is like for flow-based model, like you do the transformation until the end, while in diffusion model, you do it like piece by piece. It's more like an auto-regressive process, so the result will be more accurate. The reason for choosing normalizing flow model is because like we are targeting distribution, and normalizing flow starts from the Jacobian equation, which targets the distribution between two different distributions. It's more like somehow connected to the distribution. This is the first reason why I use like normalizing flow model. And of course, the same thing could be conducted using the diffusion model. The result should be similar, but it's just like a different way of using those. Sure. Any other question?
Yeah, I think those are all the questions we have. If you have any more follow-up questions, feel free to talk to Sean over lunch. Once again, thank you, Sean, for a great talk.
Thank you so much.